So we're going to talk about a really interesting topic today. It's one that everyone has heard about, but a lot of people don't know very much about it. We're going to talk about nuclear chemistry. So nuclear chemistry also can be referred to as radiochemistry because it involves radioactivity. Now, what's really cool about nuclear chemistry and makes it quite unique from other types of chemistry is because it does reactions that almost seem like magic. I think of it that way, at least. I think that radiochemistry is really interesting, and I also love that the math is really easy. So, you may have heard of 3 Mile Island, you may have heard of Chernobyl, you may be thinking Marvel's superheroes and superpowers. Wherever you're thinking, let's take a step back and we're going to just look at, well, what causes radioactivity to happen? So, we're going to first begin by looking at a nucleus. So I've got some plus signs on this, and those would be protons, and then I've got some things that are blue, and those are just our neutrons, because the nucleus has protons and neutrons, right? So there is something that holds the nucleus together, and it's called the strong nuclear force. This thing is insanely strong, like stronger than gravity. I mean, like insanely strong. However, it only works over short distances, namely about the distance of the diameter of a proton or a neutron. AKA, it helps hold things together because it can go from, the middle of one to the middle of the other, holds them together really, really tight. Why do we need something like this to hold a nucleus together? Because we have positive charges really, really close to each other. So the neutrons do help separate the positive charges by a little bit. If you think about electrons, those guys can't be anywhere near each other. They can't be near this distance. However, these protons are all tied up because of this nuclear force in the nucleus. Now, 2 things to think about. What happens if you have way too many protons in here? Or what if you have way too many neutrons in here? And then also, what happens if this, rather than having 4 protons, has 40 protons or 80 protons and, more than 80 neutrons? How well does that strong nuclear force work? Well, it still works well at holding atoms together, but there comes to a point where if you've got a force that's just holding individuals together and you've got lots of them all in there, you can start having some issues with instability. And that's where radiochemistry, nuclear chemistry, that's where our radioactivity comes from. It's when you have some instability and the atom is trying to fix itself. Now, what the atom can do to fix itself is crazy, and you're going to learn about that in another lesson. But the atom can do some crazy things to fix stability issues. I'm going to jump over here. Before I move on further, you also need to know that isotopes play a role in whether something's stable or not. Rather, what I should say is some isotopes are stable and some are not. So remember this bottom number from General Chemistry 1 represents the number of protons. And remember that the number of protons tells us what element it is. So the protons give the identity of the element. If an atom fixes itself in a way that the number of protons changes, the element changes. Oh yeah, that's insanity, but it's exactly what happens. So if you look at isotopes, isotopes are different versions of carbon. This is carbon 12, neutrons plus protons. So if I subtract them, you can see this has 6, 7, and 8. This one is 99% abundant, this is 1% abundant, and this is a tiny, tiny percentage abundant, and it's radioactive. So why would this one be radioactive and the other one's not? It is related to neutron protons, and it's also related to more than neutrons and protons. But it is going to be related to that kind of a ratio. I'm going to zoom over here and we're going to look at this. So what this is a chart that tells us the number of neutrons and the number of protons, and it tells us things about stability. So right here I've got neon in here, and if I zoom in, neon, this would be 10 protons, which is what makes it neon, and then 10 neutrons, so 10 plus 10 gives us 20. So this is where that neon would fall if it has the same number of protons and neutrons. This is where calcium falls if it had 20 protons and 20 neutrons. This is where tin would fall if it had 50 and 50. And then this is where mercury would fall if it has 80 and 80. So let's take a look at our key though. Our key shows us non-radioactive versus radioactive, basically stable versus not stable. If it's not one of those colors, it doesn't exist. It's so unstable, it can't even be. So if we take a look over here, you can actually see that in this range of elements, This is not talking about abundance. Keep that in mind. We're just talking about, is it possible for it to even be there, even if it is radioactive? You will see that this tends to run higher than the line. So the line is equals protons and neutrons. So what this is telling us is that it tends to be that you want to have more neutrons than protons, especially as you get heavier. So that's one thing. Note, though, that our stability ones, they kind of make these little funny lines. It's like, why is just that little section stable? Well, we have something called magic numbers of stability. I love the way that sometimes some chemists have just really creative ways of talking about things. So they call these magic numbers. And what we've found is that when you have these numbers of protons, you end up with like special stability. Now, this course is beyond explaining all the details of that. But if you want to Google it, go for it because it's interesting stuff. Just want to point out that 10, which is the protons being 50, has 10 stable nuclei, but the elements right around it only has 2. So there is something about this 50 protons being super stable. The other thing I want to point out is that right down here, this is the last time that we even have anything that's stable. So that's 82, and 82 is lead. Any element after lead is going to be radioactive. So this is one thing. It has to do, one of the issues with something being stable, it has to do with more neutrons than protons. Another issue, it actually is the opposite. If you have more protons than neutrons. And then the third issue is going to be just basically too large of a nucleus. Meaning too many protons. All these things lead to instability. When you've got things that are unstable, what you have is a nucleus that's going to want to change. So how does a nucleus change? A nucleus can actually change protons into neutrons into protons and protons into neutrons. It's some crazy stuff. Stay tuned.